This one is good? By the way, who was here last year? If you can raise your hands. See, this is the picture you need to take, by the way, DK. Everyone's sitting in the same place that they did last time. I see it, but I don't see it. Right. It's like Santana is sitting in the same place. I think Karen was sitting there. Adam is missing, but he's sitting there, right? It's like everyone is this on. You should take a picture and put it for next year.
Reserve seats.
Exactly. That was funny. Okay, so I've 30 minutes more or less. There is several topics I wanted to go with you, and I'll try to make it on time. So first, well, I need. We'll go here. So one thing that, from Mellanox perspective, we're very proud for the last top 500 list is because I think for the first time InfiniBand had the top 3 systems on the list. So the number 1, which is the core system at Oak Ridge, number 2, which was the previous number 1 at Wuxi, China, and then number 3, which was the second core system that was deployed in Lawrence Livermore. No, I need okay. So that was the top 3 systems. And then also interesting systems on the list. The one on the left is the fastest AI system in Japan. And then we have the fastest supercomputer on industry level, which is ENI, oil and gas company in Europe. There was the fastest in Canada. And I think probably not less interesting is kind of the first large-scale ARM system. That was not on the list, but it's supposed to be on the November top 500 list. And that's actually the first large-scale ARM system deployed for HPC research or development. Let's see if this works. Okay. Wanted to start a little bit with the in-network computing, and then we're going to expand from there to other places. It's a high-level slide that kind of emphasizes the area that Mellanox is focusing on. In the past, data centers or systems were deployed in a CPU-centric architecture, which means if you want to analyze data, you need to move data all the way to the CPU. And that's great bottlenecks, or new kind of bottlenecks. So in the early years, Mellanox's approach was, let's start with the network functions, and then move all the network functions from the CPU to the network, and with that we can free CPU cycles. So we started with doing transport on the networks and then putting RDMA and other aspects like that. In the recent years, the focus is, after we finish with the network functions, is actually to move and put data algorithms on the network. And the reason to move data algorithms on the network is because you are getting into performance limitations of forcing moving data to the CPU before you can do something on it. And if you start moving data algorithms to the network, you can actually solve those kind of bottlenecks. The network definitely will not become a general purpose CPU, but a lot of data algorithms, they required data that comes from multiple processes together, such as doing aggregation or reduction or other things of that sort. You can actually run those on the network and achieve much better performance. I'm not going to go through the product lines. I'm just going to mention one thing, is that we have a new product line that we start shipping early this year, which is called BlueField, a system on a chip. And I will have some slides to talk about BlueField. So going back to the in-network computing area, there is some main items or major items that we support today. The one in the middle is called SHARP, or Scalable, Hierarchical, Aggregation, and Reduction Protocol. That's actually the capabilities on the switch fabric to run data aggregation or reduction protocols. So you can do reduction, or reduce, or barrier, broadcast, or gather, and so forth, and run those operations on the network instead of running those on the CPU. On the general MPI side, we do support MPI tag matching in hardware. And as you move MPI tag matching to the hardware side, you can actually move the rendezvous protocol to the hardware as well. So multiple MPI functions are actually migrating themselves to the network because of performance or achieving high performance. Shield is a different technology that aim to accelerate network recovery because of errors. I think I mentioned that last time I spoke here, so I'm not going to go into details around that. There is NVMe fabrics and NVMe emulations and so forth, utilizing RDMA capabilities and many other items. So the vendor did a tutorial on Sharp yesterday, the vendor. So he kind of went into details on everything. I'm not going to go through too much here. I'm just going to mention a couple of things. The first thing is that the first Sharp implementation on the EDR switches was focused on small messages. Now you can aggregate small messages into larger messages, but the focus was small messages kind of for the HPC workloads, more or less. They wanted it released with HDR switches, extend that to large messages. And the reason to extend it to large messages is also to extend the support for doing deep learning algorithms or the reduction for deep learning as well on the network. So a few results about Sharp. This is running an AllReduce operation on a system from 2 nodes all the way to 128 nodes. The left side is doing 8 bytes or 128 bytes of AllReduce. Dash line is the software, and the solid line is the hardware, and that's the difference in latencies. On the right side, it's 1 kilobyte or 2 kilobyte of reduction. Here, I think it's a more interesting performance result. This is tested on University of Toronto, or SciNet, which is a 1500 node, the first large-scale Dragonfly InfiniBand system out there. Again, MPI reduce on the left side, and it's running on a full 1500 nodes. On the left side is 1 ppm, so you have 1500 MPI regs, and you see the software latency versus the hardware latency, and according to the bytes or the size of the message. On the right side, I think it's probably more interesting because this is 40 ppms, or 60,000 MPI regs running on the system. And again, you see the difference in latency between running things on the software side versus leveraging the capabilities within the switch network to do the reduction operation. If you take it to Oak Ridge, for example, I think that the AllReduce latency on Titan, it's around 92, 93 microseconds, more or less. And then one on Corals, I think they're in the 6 microsecond range. That's the difference. Now, as we start also looking on AI and deep learning, main reason is because it's actually using the same technology for both HPC and AI. Then when you do a training in deep learning or parallel training, you have the training agents that calculates the difference between, calculates the weights or the differences and then provide back the differences in weight. And there is an entity that runs on the CPU that's called the parameter server that gets all the difference in weight and the reduction of that operation, and then send back the new weights to the training agents, which go again and again and again. So actually it's the same AllReduce operation. And you can replace the parameter server actually with a switch that does the AllReduce operation by itself. So instead of putting CPU or putting parameter servers, you can actually run that part of the training items on the network instead of running that on a CPU. A side effect, by the way, of running the reduction operation on the network is the reduce of data motion. So you have less data to move, which means less congestions and things of that. I wanted to spend a few minutes about a different topic that it's not directly related to the MPI side, but it's actually related to the system and how you run jobs on a system, or talk a little bit about network topologies. One of the good things in InfiniBand is InfiniBand was born as the optimal SDN fabric before people knew what SDN is. And SDN means that you can actually program any routing that you want or program the switches to build any sort of topology. Many of the topologies out there are fat trees or variations of fat trees, of blocking or non-blocking or islands of fat trees and so forth. HP or SGI and HPE created Hypercube or Nance Hypercube, which is kind of a Dragonfly kind of a version, and they have that deployed in many places. Some folks also build Tauruses. I think Sandia at some point built a 5,000 node Taurus system. Taurus is a good topology, for example, for stencil or QCD applications. And then there is Dragonfly. And for years, Dragonfly was associated with Cray. Right? Cray had Dragonfly, and if you wanted Dragonfly, Cray was the one that built Dragonflies. But nothing hold InfiniBand to support Dragonflies as well. So we put some effort around enabling Dragonfly. The main difference is with the Dragonfly version that we came out, and the one that Cray has built, is that Dragonfly builds upon creating groups, and then those groups are created within a full graph. So the Cray Dragonfly, it's actually putting a Dragonfly within a group, and then those groups are connected in a Dragonfly. Our design, which we call Dragonfly Plus, actually use factories within the groups, and then those groups are connected with a full graph. The reason that we went with factories inside of the group is because we figured that you can reduce the number of worst-case switch hops that you need to go across, and that means that you can get lower latency versus the Cray implementation of Dragonfly.
So, is this like a Dragonfly of switches?
So all the groups are connected with a full graph. So yes, it's a Dragonfly. Inside of the group, you can do whatever you want, by the way. You can do torus within a group. You can do factories. You can do hypercubes within a group. Whatever you do with the group, it's your own decision. Now, if I look on the kind of the literature view of Dragonfly, that's how it looks like. So you have the groups here, and then you have the full graphs that connect all of them together. Now the question is why should I go to Dragonfly, or where should I use Dragonfly, and so forth. Performance-wise, factories and Dragonflies actually give the same performance. You can build blocking oversubscribed factories. You can build oversubscribed Dragonflies. There are two differences. One of them is cost of a system. And when you go to system sizes of, let's say, 700, 800 server nodes, Dragonfly become more cost effective. Shorter cables and things of that sort. So beyond that size, it's become more cost effective. Below that size, factories are more cost effective. Beyond that part, one of the good advantages of Dragonfly is that if you want to expand the system in the future, Dragonfly gives you the simplest way to do it. Meaning, if you build a factory system and at some point you want to expand it, you need to do two things. Either you had to do reservations beforehand, a plan for that expansion, or second, you're going to recable the cables in the system, which is a heavy lifting job, and not everyone likes to recable the system. In a Dragonfly scenario, that's completely different. I'm going to take you through some of the steps here. So if this is kind of the literature view of Dragonfly, I'm going to change some of the structure here. So I'm going to take the second level of switches and just put them in different groups, which is like this. So it's the same Dragonfly. The thing is that those are part of the groups, and then part of the other group is here, and then there is the blue connectivity between them. And when you look on building a Dragonfly, this is actually how you do the implementation. So the node sits here, and then this is where you put kind of switches and build the core Dragonfly network. And once you do that, if you want to expand the system in the future, it's very simple. The only thing you need to do is adding more switches to cores. So you don't need to recable any of the long cables. Those stay the same. You just need to do some recabling within the rack itself, which is very short cables. And then you can add as many groups as you want. And this is, by the way, something that we didn't figure out before we actually went and implemented the first large-scale system. The University of Toronto planned to have, in the beginnings, they planned to have like 3 groups connected together. Later on, they came with the 4th group. And then we noticed that actually to add more groups is very easy. You don't need to recable anything. So that's one of the big advantages of Dragonfly. Another topic, HDR InfiniBand. So we're starting to ship HDR InfiniBand, and we're going to start seeing multiple systems being deployed out there. There was a discussion on Joules before. I missed the guy. So Joules is an EDR system. It's going to move to HDR. I'm not sure it's here. But there's other multiple systems. Oh, sorry. But there's other systems as well that's going to start building with HDR. Just a few things. The HDR devices comes with, or there are two HDR devices. One of them is Connectix 6, 200 gigabit per second, supports all the way 100 gigabit and so forth. PCI Express Gen 3, PCI Express Gen 4. Connectix 6 comes with a socket direct capability, which means that you can connect single NIC to 2 sockets or more directly. So you have low latency from each socket directly to the network. You don't have the remote socket or local socket approach. And multiple new accelerations as part of the in-network computing, accelerations to all and other operations. And then the switch, which is called Quantum, comes with 40 ports of HDR or 80 ports of HDR 100, which are 100 gigabit per second speed, 90 nanosecond latency, and the Sharp V2 version of it, the ability to do data reduction or aggregation for small messages and large messages. And then the Modular switch that comes with it, it has 800 ports of HDR or 1600 ports of HDR 100 in one big chassis. Few words about BlueField. So BlueField is a new product line from Mellanox. So we have the adapters, the switches, the cables, and then BlueField. BlueField is a system on a chip. It's a combination of the first BlueField that we start shipping earlier this year. It's an integration of Connectix 5, which is the EDR adapter with all of the accelerations in it. 16 cores of ARM A72, 2 DDR4 channels, PCI Express Gen 3 and Gen 4 switch, and the rest of the things that related or required there. BlueField as an SoC aimed to go to 2 different areas. One area is the ability to build appliances which require very strong network RDMA capabilities and some CPU to manage the box. For example, NVMe fabric boxes. The other side is building elements that are forming the Smart NIC product of line. Smart NIC, it means that you have a network adapter which has compute elements on it. So not just you can use the network acceleration within a network, but now you have 16 cores that you actually can program them to run different kind of algorithms directly on the data, directly on the NIC. And you can get the data comes from the network and do something with it and then put it to the CPU or inject it back to the network and so forth. So you can do very interesting things with it. And from that reason, there's multiple products that you're going to see from Mellanox or already see from Mellanox. There is the BlueField platform, which is an ATX form factor for people that wants to test BlueField, program BlueField, play with it, and so forth. There are 2 smart NICs options. One of them is focused on Ethernet, 25 gig, hyperscale cloud infrastructures. The other one support both Ethernet and InfiniBand up to 100 gigabit per second speed, because that's what you have on Connectix 5. And this is where you can run algorithms and program that to do interesting things, as well as to move more elements from MPI, for example, to run directly on the network adapter. So that might be a good things of exploring. We also have multiple companies that are building right now storage controllers, and that goes to NVMe fabric boxes. BlueField has NVMe fabric offloads, and you can use it actually to build a complete JBOFs. You just put the SSDs connected to the integrated PCI Express switch. You have the RDMA network adapter and the CPUs. So the storage is this kind of a flavor for building NVMe over fabrics or remote NVMe. There's also some work around security. If you look on a cloud infrastructure or security infrastructures, for example, the network services that today run in a hypervisor actually can run on BlueField. Or the storage services or the security services, those elements can actually run on the network directly. So we see that as enhancing networking capabilities, security capabilities, and also providing capabilities to run different kind of algorithms. that are more related to HPC workloads on BlueField. So if there is any interest to work with us on BlueField for those different scenarios, please do approach me. And then some final words about UCF, which is kind of a new old thing, more or less. The work on UCF itself is a non-profit consortium that was finally established a few months ago to run or manage different kind of programs or collaborations. There are two projects right now that one project and the second one is now being built under UCF consortium. The first one is UCX. So UCX is something that was developed for quite some time right now, and there's multiple releases, and I'm going to talk a little bit about UCX. The second thing is we're now building an open RDMA community under UCF. So if you know Jason, one of the Linux maintainers, and Liran Liz, for example, they're going to start leading the RDMA work within, or the RDMA project within UCF. Board members, several board members. You see the DOE Labs, commercial NVIDIA, IBM, Mellanox, AMD, ARM, DK, and some other peoples that sits on the board. So one of the first projects of UCF, and getting that to actually to create specification for that, is UCX. And UCX, looking on the history back, UCX was created in order to take multiple communication frameworks that were developed from different entities and actually to create one that can support any kind of networking, and it's a low weight and it's easier to use, and actually that's kind of the next generation of what we see from a framework perspective, a software framework perspective. So the motivation was not to create a new one, not to create a new one that actually match a proprietary network, and we might expand that to do other things, but the goal is to combine multiple frameworks and support any sort of networking infrastructure underneath. So the elements at the beginning were, or the combination at the beginning was combining MXM, which what Mellanox created, UCCS from Oak Ridge, and then PAMI from IBM, and that's going to serve as a first integration, and from that point, adding capabilities and enhancing UCX. UCX provides multiple things. First, the idea is to provide an API that works on everything. So you can run InfiniBand underneath of that, you can run Ethernet underneath of that, you can run Rocky underneath of that, you can run NUMA, you can run the Cray networks and any other sort of networks. Performance focused, community driven, so it's not kind of focusing on one element, it's enabling something that runs across everything. So UCX as a framework, it's a framework of APIs. We see that more and more being now deployed in many systems. We expect that all of the InfiniBand systems actually going to start running UCX as a de facto framework. We're seeing that stuff happening in the DOE labs. We expect that all the Ethernet systems will run on UCX, and so forth. So that's where all the community work is focusing on. I'm not going to go through that, but it's high-level overview of the framework itself. We had a good BOF session at the International Supercomputing Conference, which was videotaped, which included me, but I was the kind of the less important speaker. It's included Pasha, which is going to talk in an hour or so, I think, and he also is going to talk about UCX and UCX on ARM, and the performance that we're seeing with UCX on ARM. And DK Panda was part of that. So that video is going to be posted on the website very shortly. Bottom line, UCX, it's results of full community effort. It's provides probably the best performance that we're seeing today. It supports any kind of network, and then each company can decide what they want to support or not. But today it runs off on the InfiniBand, and that's the future of the framework on InfiniBand. On Internet, the Luma stuff, the Cray Gemini and Aries, and so forth. And as I mentioned before, partially I think going to show some performance numbers on UCX. And with that, I want to thank you for listening.